Hello everyone. Today we are going to do section 9.4, vectors in 3 dimensions. We already know that vectors are objects which have two properties. They do have magnitude or length and direction. So far you know that we can have vectors on the plane, right, in x and y coordinates, but the same vector with magnitude and direction looking like an arrow can be placed in space, in three-dimensional space. So let me draw the picture of how we draw three-dimensional coordinate system, guys. It's going to look a little bit different from two-dimensional coordinate system. Please watch how I do this. And normally that's how we are going to do it. So we are going to label the axis which looks toward me as x-axis, the axis which goes to the right as y-axis, and the axis which goes up as z-axis. Well, there's going to be origin in the beginning, so three coordinate plane axis. And if you do have a point in space, you can connect it to the origin and make up a position vector like we were doing in our two-dimensional space, right? I'm going to label it vector V. Same way we were doing two-dimensional vectors, three-dimensional vectors are going to have components, right? I'm going to write it down. So components of vector V are V1, V2, and V3, three numbers instead of two numbers, right? Because in two-dimensional space, we had x and y, and here we add one more coordinate. So we are going to have one more dimension for the vector. So we call V1, V2, and V3 components, right? Like we have in three-dimensional vectors, and they are basically the coordinates of endpoints. Endpoint of the vector. What we have over here is called the position vector. Position vector is vector which starts at origin. Is it necessary for vectors to start at origin? No. Remember that vectors with same magnitude and same direction are equal, and if you take this vector, pick it up and move it anywhere in space, it's still going to be the same vector. Let's see how do we calculate components of a vector if somebody gives you initial and terminal points. So let me write down a couple of points. Imagine somebody gives you coordinates of point P, three coordinates, right? Because that's three-dimensional space. We have x, y, and z. And coordinates of point Q, 3, 1, -1. And they're asking you, what is going to be position vector PQ? So how to write down PQ in the form of components. Here we have like two pairs of three coordinates, a pair of three coordinates, right? So, well, remember that P is initial point. And Q is terminal point. So actually vector PQ is going to look like this. It's going to start at point P and end at point Q. I get some dots unnecessary on my whiteboard. Okay, so how do we calculate the position vector or components of this vector PQ? Well, the general kind of rule is subtract initial from terminal. I'm going to write down terminal minus initial. In our case, what are we going to have? Terminal point is Q, right? So it's 3 x coordinate of terminal point minus 1, and then 1 minus -4, and then -1 minus 5. When you just calculate the numbers here, and you're going to have what, 2 here, right? 1 minus -4 is 5. 1 plus 4, right? And -1 minus 5 is -6. So this is component of vector PQ. Okay, so how do we calculate the magnitude of a vector? In two-dimensional space, we just like square x coordinate, y coordinate, and get a square root. In three-dimensional, for 3 dimensions, we are going to square x, y, and z. So let's talk about magnitude. Magnitude of a vector. Well, again, let's consider vector V. which has components v1, v2, and v3. Remember that magnitude of a vector is just a length. It's just take a ruler, put it one side of the ruler with 0 at P, and see where Q comes. Like, is it 2 inches, 5 inches, or 2 kilometers? Well, usually to calculate distance between 2 points, what we do? We calculate distance using distance formula, right? But position vector or components is very convenient vector because it already has like x2 minus x1, y2 minus y1, and z2 minus z1, right? The differences we use for the distance. So we just need to square actually the components of position vector, and that's going to give us magnitude. I'm going to write down that usually we use straight brackets for magnitude, and that's going to be a square root of the first component squared plus the second component squared plus the third component squared in the square root. So basically it's just a distance. Okay. Well, let's try to calculate kind of length of something. For example, the vector we have over here, we already kind of found that position vector PQ is 2, 5, and minus 6, right? Let's calculate actually what is going to be the length of this vector. So I'm going to put vector into my straight brackets, 2, 5, minus 6, and kind of just put the components into square. So it's 2 square plus 5 square plus negative 6 square and the square root, and it's going to give us a square root of 4 plus 25 plus 36, which is going to give us something like a square root of 65, I think. Maybe I'm wrong, guys. Watch my lectures carefully, okay? Okay, so we know what is magnitude, we know how to find position vector. Now, let's talk about algebra of vectors. What can we do with vectors? Actually, we can do a lot. The only algebraic operation we cannot do with vectors is division. All other operations are possible. So I'm going to change my color to talk about algebra. So algebra of vectors. Well, we are going to use two vectors as examples. Let me erase the bar, which we don't need. So I'm going to consider vector v. This is one of my favorite vectors with components 1, 2, 3. And a vector u, which is my second favorite vector, and it's 4, 5, and 6 components. And I'm going to show how to add these two vectors. So we add vectors by adding components. So if you want to add vector v plus vector u, I'm just going to add components. 1 plus 4, x component separately, 2 plus 5, y component separately, and 3 plus 6, z components separately. And after you add them, you are going to have 5, 7, and 9. So that's a sum of two vectors. How do we subtract vectors? Number 2. Well, for example, I subtract vector u from vector v. You can subtract vector v from vector u. Same way, we just subtract components. And in our case, it's 1 minus 4, 2 minus 5, and 3 minus 6. In this case, we are going to have what? Minus 3 and minus 3 and minus 3 again. Well, just because they are shifted like 3 units, right? Let me erase unnecessary stuff. Well, what else can we do with vectors? We can multiply vectors by a scalar. Scalar is just a number. Number does not have a direction. It's kind of just magnitude, no direction. So imagine that our scalar equals like 3. And what we can do, we can, for example, multiply vector by a scalar. You see the difference between vector and scalar? I put a little bar above the vector and nothing about the scalar. Scalar is just a number. Well, it comes from the word scaling. Scaling means a stretching or making smaller by certain amount of times, right? So I'm going to multiply vector v by scalar 3. So it's 3. And then I copy vector v, 1, 2, 3. How I do this? I just multiply every component by 3. So it's 3 by 1, 3 by 2, and 3 by 3. Well, I'm just going to calculate where I'm going to have 3, 6, and 9, and that's my final result. So I multiply vector by a scalar. What else do we need to know about vectors? Well, I'll need to go to my next page and give me guys a second. I'll need to save this one because I'm afraid it's going to kind of yeah. Okay, I'll need to go to the next page. Okay, give me a second. So there are three important vectors in three-dimensional space, which we call basis vectors. Let me draw coordinate axis again and kind of show what are my special vectors. So my special vectors are unit vectors along axis. So you take like 1 inch and move 1 inch along x-axis and call this vector I, and move 1 inch along y-axis, not necessarily 1 inch actually, you can move 1 centimeter or 1 kilometer. And along z-axis, it's going to be vector k. Does not kind of squeeze into it. So length of each of these vectors I, j, and k is 1 unit. And you see that they are perpendicular to each other, right? Because x-axis is perpendicular to y-axis, and y-axis is perpendicular to z-axis, and z-axis is perpendicular to x-axis. We call them basis vectors because they're a very convenient way to express other vectors through them. I'm going to write down coordinates of each basis vector, but I don't want to use yellow color. Yellow color is not visible on this board, actually. So I'm going to write down what are coordinates of I vector. Well, x coordinate is 1, right? Because it has no y or z components, y and z coordinates are going to be 0 and 0. And sorry, my bracket is not very good. For j vector, we have only y component, and x and z components are equal to 0. And for k, we have only z component. So x and y are equal to 0, and z component equals to 1. How can we use these basis vectors? We actually can express any vector using basis vectors. Let me show you something. Imagine that somebody gives you a next sum of 3 vectors. 1i plus 2j. Sorry, I put a wrong place bar over here. Bar is supposed to be around j, not around 2j and plus 3k. Well, sum of 3 vectors multiplied by scalars 1, 2, and 3, right? And vectors are I, j, and k. Let me see if I kind of do multiplication and add them, what I'm going to have. I'm going to start with the first one. So it's 1, and the vector is 1, 0, 0, plus 2, and the vector is 0, 1, 0, and 3, and the vector is 0, 0, 1. We remember to multiply vector by a scalar, we just multiply every component by this number, right? Because these two components are zeros, we're not going to do anything to them, but we're going to multiply this 1 by the first component x, right? And we're going to have 1, 0, 0. For the second one, x component is 0, so it's not going to change when multiplied by 2, but y component is going to change, and that's going to be 0, 2, right? Because we multiply 2 by 1, it's 2, and z component is still 0. For the last one, we're going to multiply by 3 only last component, right? Because first two components are equal to 0. Now I'm going to use addition rule for these 3 vectors, right? I add x components, y, and z components. Because my x components for vectors 2 and 3 are zeros, you see 0 here and 0 here, so I'm going to just have 1. Y components are 0 for the first one, there is 0 here, and 0 for the second one, so the only 2 is coming from the second vector. And z components are zeros for first 2 vectors and 3 for the last one. Well, guys, what do we see actually? If you look carefully at this vector, you are going to recognize actually our vector v, which was 1, 2, 3. But if you look at the way we write it down through basis vectors, you're going to see that actually the very same numbers appear in front of my basis vectors. So 1, which is x component, appears in front of I, 2, which is y component, appears in front of j, and 3, which is z component, appears in front of k. So we are going to get a new way to write down vectors. We can write it down as like 1, 2, 3 in brackets, or we can use vectors I, j, k to write the very same vector. I'm going to show you just one example of doing this. Imagine somebody gives you a vector -2, 1, 0, and they're asking, write it down through basis vectors I, j, and k. So what you are going to do? You're going to do -2i plus 1j plus 0k. Well, do we need to write actually 0k? No, guess it's not necessary, but if you write it down, no one is going to complain. That's a different way to write down the three-dimensional vector. Okay, what else do we need to know about 3D vectors? Remember that for 2D vectors, we had dot product, and there was a product of x coordinates and y coordinates, right? Here, because we have 3 coordinates, we are going to also have a dot product, but it's going to be a product of 3 coordinates. So the dot product. Imagine that we have my 2 vectors with components v1, v2, and v3, and my second vector is u with components u1, u2, and u3. Then by definition, dot product between vectors v and u, a little dot between them, is equal to a product of components v1 by u1 plus v2 by u2 plus v3 by u3. Dot product is a scalar. Scalar means that it does not have a direction. It has only magnitude. Okay, so I'm going to write down scalar. Well, let's try to find actually the product between some vectors, right? I'm going to use my favorite vectors. Vector v is 1, 2, 3, and vector u is 4, 5, and 6. So let's find the dot product between vector u and v. Well, we multiply 1 by 4 plus 2 by 5 and plus 3 by 6. And if you do this multiplication, we are going to get 32. So my dot product is equal to 32. You see, 32 is not a vector. It's just a number. It does not have any direction. You remember from two-dimensional vectors that dot product can be expressed through the magnitude of the vectors and the cosine of the angle between them. Imagine that you have two vectors, like vector v and vector u, right? We do have the angle here. In 2 dimensions, we know that dot product between vectors u and v equals magnitude of vector v by magnitude of vector u and by cosine of the angle between them, right? Well, the very same property is going to work for 3-dimensional vectors. Just there is no difference for vectors, 2-dimensional or 3-dimensional. What is good about dot product for us? All the properties of dot products are going to stay same, which means, for example, you can calculate the angle between two vectors using dot product. I'm going to maybe change my color and erase extra dots I have over here and write down how can we use this. For example, we can write down that cosine of the angle between two vectors, it's a dot product between these two vectors divided by the length of the first vector and length of the second vector. Well, this way we can find actual angles between two vectors, right? Why don't we practice with our known vectors u and v and see how it's going to work? We already do know the dot product between u and v, it's 32, right? We just need to know the length of vectors. Length of vector v, it's a square of each component and the square root. And length of vector u, it's a square of each component. And the square root. So we are going to have 32 over square root of 14 and square root of 77. Well, it's not the angle yet, right? It's going to be cosine of the angle. To find actual angle, we'll need to find cosine inverse, right? To find theta, we'll need to take cosine inverse of this 32 over square root of 14 multiplied by square root of 77. Well, I think I'm going to stop my recording for a second, calculate it, and write it down over here, okay? Give me a... Okay, guys, so I did my calculations. I divided 32 by square root of 13 and square root of 77 and took cosine inverse, and my result was 12.9 degrees. A very convenient way to find actual angle between two vectors, right? Let me move to the next page and talk about one more property of dot product, which, remember, can tell you whether two vectors are perpendicular or not. What do we know about perpendicular vectors? If two vectors like u and v are perpendicular or have 90 degrees angle between them, what happens to the cosine of the angle? Well, we remember that cosine of 90 degrees equals to 0, right? But according to my formula, dot product of u and v equals length of vector v by length of vector u by cosine of theta. So if two vectors are perpendicular, this one is 0. No matter what is u and v, if they are non-zero, then the product, the whole thing is 0, means that the dot product is 0 too. What does it mean? It's a convenient way to check if two vectors are perpendicular, again, knowing if dot product is equal to 0 or not. Well, let's consider some vectors and just check if they are perpendicular or orthogonal or not. Give me a second. For example, I'm going to consider a vector v, which is 2i plus 3j plus 5k. And I'm going to consider vector w, which is I plus 2j minus k. And I want to answer the question whether they are perpendicular or orthogonal. Are they? Okay, give me a second. I have lots of extra dots, which I don't like to have on my screen. Okay, what I'm going to do, guys, the way with ijk is not very convenient to use, so I'm going to write it down in components form. Remember that whatever sits in front of I is x, whatever sits in front of j is y, and whatever sits in front of k is z. And here we have 1, because there is nothing, means that it's 1, not 0, right? It's 2 in front of j and minus 1 in front of k, just because it's minus k, right? Now I can find the dot product between these two vectors and see if they are perpendicular or no. So dot product between u and v and w is going to be 2 multiplied by 1 plus 3 multiplied by 2 plus 5 multiplied by negative 1, right? If I kind of simplify it, that's 2 plus 6 minus 5. Well, we see it's 3, which is not equal to 0. They're not perpendicular. Okay, or non-orthogonal. Extra dot, which I don't need. Now, well, we need to consider example where they're perpendicular, right? Just to see like how it works. I'm going to write down another vector, vector u, and that's going to be slightly different vector. Vector u is going to be 2i plus 2j and minus 2k. If I write it down in components form, it's 2, 2, and negative 2. Let's check if dot product between v and u is 0. Are they perpendicular? Well, we remember that 2 multiplied by 2, right? 3 multiplied by 2, and 5 multiplied by negative 2. What we are going to have? We're going to have 4 plus 6 minus 10. Well, obviously equals to 0. So they are perpendicular. Two vectors are perpendicular. You see, easy way to check if two vectors are perpendicular or not. The last thing we are going to learn about 3D vectors is direction angles and direction cosines. You remember from 2D that vector can have an angle with positive direction of x-axis. Well, you can also calculate an angle with positive direction of y-axis, but because we know that they have like x and y have 90 degrees between them, does make sense actually. If you know that the vector makes 30 degrees with x-axis, you know that it's automatically making 60 degrees with y-axis, right? In 3D, it's slightly different, and we are going to have 3 different angles. So they call direction angles or direction cosines. I'm going to, let's use orange. So direction angles and direction cosines. Well, we're going to start with direction angles, but usually people calculate only cosines because everyone knows how to use calculator and take cosine inverse, right? Sorry, I got some dots which are necessary. Well, imagine that we do have a vector v, right? And there's x-axis, y-axis, and z-axis. Let me change the color to label my angles in different color. So vector v is making angle alpha with x-axis, is making angle beta with y-axis, and angle gamma with z-axis. And these angles, alpha, beta, and gamma, are called direction angles. Very nice, right? Usually, like, direction angles are telling you which direction the vector looks at, right? How to calculate these direction angles? That's where we need direction cosines, actually. For example, how do we calculate angle between vector and x-axis? Well, we do have a little vector along x-axis. You probably remember it's called I. So why don't we calculate angle between vector v and this vector I? So alpha is angle between v and I. So how do we calculate it? Using cosine, right, and dot product. V multiplied by my second vector, which is I, by the length of vector v and length of vector I. Well, we do remember that length of vector I is equal to 1, right? So actually we are going to have only vector v in denominator, length of vector v. Also, if you do multiplication of vector v by vector I, let's do it once in general to get the idea. Imagine that vector v is equal to v1, v2, and v3 components. And we remember that vector I has components 1, 0, and 0. Dot product between these two vectors is going to be what? Well, v1 multiplied by 1, and then the rest, v2 and v3, are going to be multiplied by zeros. So they're going to not participate. And the cosine of alpha equals just x, coordinate of the vector, by the length of the vector. Now, maybe we don't need to calculate gamma and beta just because they are exactly similar, and I'm just going to write down the formula for them. So cosine of beta, well, beta is a second angle, is going to be what? V2 over length of vector v, and cosine of gamma is going to be v3 of the length of vector v. So these cosines are called direction cosines. And actually, if you want to know direction vectors, direction angles, you will need to calculate cosines first and then take cosine inverse and calculate angles. Okay? I think we can calculate direction cosines for my favorite vector 1, 2, 3, right? I don't want to do calculate direction vector because this I have to do the pause and go to calculator, but you can guys do it. So my vector v is, again, vector 1, 2, 3, right? I know that length of my vector v is a square root of 14. I calculated it somewhere in the beginning, so I think everyone still remembers it. My 14 does not look like very nice 4. I'm going to fix it a little bit. 14. Right now, what is going to be cosine of alpha? Well, x component 1 over the length of vector v. Well, again, I can always find alpha by taking cosine inverse of 1 over square root of 14. I'm just too lazy to do this. Okay, now cosine of beta is going to be what? Y component 2 over square root of 14. And cosine of gamma is going to be 3 by square root of 14. Okay, so basically we did calculate the cosines. Usually no one is asking about actual angles, but interestingly that cosines of direction angles are going to have a special relation between them. Well, let's check one thing right now. I'm going to move this over here so it's not going to distract us. And let's check one thing. Let's square, sorry, change it to razor. Let's square for this particular one cosine of alpha, cosine of beta, and cosine square of gamma. Let's see what we are going to have. If we square this one, it's going to be 1 over square root of 14 squared plus 2 over square root of 14 squared plus 3 over square root of 14 squared, right? Well, 1 squared is 1, right? Square root of 14 is just 14. If you square root of 14, right? 4 here, we have 4 divided over 14, and here is going to be 9 divided over 14. If you bring them into one fraction, what are we going to have, guys? We're going to have 1 plus 4 plus 9, which is going to be 14 over 14, or 1. So actually sum of squares of direction cosines is going to be equal to 1. Is it going to happen for all vectors? Well, let's look why did it happen for this specific one. You see that when you square the cosines, it's like denominator is going to be the length squared. And the numerator, you are going to have x squared y square and z square, which are going to give you the length again, the length squared. So that's the reason why it's equal to 1, because you have length square on the top and length square on the bottom. And that's why this is going to be the true statement. So I'm going to maybe write down equals to 1 and kind of round it up. So guys, this is analog of Pythagorean identity for 3D world. In 2D world, we have cosine square alpha plus sine square alpha. Here we have cosine of square alpha plus cosine square beta and cosine square gamma. Why don't we have a sine? Well, actually, guys, if you remember, for two-dimensional vectors, we just define one vector, right? Direction vector and one direction angle, and that's angle between vector and x-axis. We know that the angle between vector and y-axis is complementary. For example, if this is 30, this one is going to be 60. But cosine of 60 is exactly sine of 30, and that's why we have sine in Pythagorean identity in 2 dimensions, and all the cosines in Pythagorean identity for 3 dimensions. Okay, guys, that's all for this lecture, and I think we can finish at this point. Please do your homework, and I don't think that that's too much of the homework, right? Okay, let me stop.